You know, every single time you go online, you're using this incredible system that you've probably never even thought about. But it's arguably the most important part of how the internet works, your IP address. It's like this invisible engine connecting you to everything. And today, we're going to pull back the curtain and see exactly how it all comes together.
I mean, really think about it for a second. You type a website into your browser, you hit enter, and just milliseconds later, a server that could be thousands of miles away sends information right back to your screen. How in the world does it know where you are? How did your request even know where to begin to go?
Well, the answer is a system that works a lot like the old-fashioned post office. Every single device connected to the internet, your phone, your laptop, your smart TV, it gets its own unique address. This makes sure that the little packets of data we're constantly sending, you can think of them as digital letters, get delivered to exactly the right place, and, crucially, they know the return address to get back to you.
So let's break this down. What exactly is this digital address, and what are the rules of the road that keep the entire internet from just collapsing into total chaos?
Okay, so its full name is Internet Protocol Address. Now, the word protocol sounds super technical, right? But really, it's just an agreed-upon set of rules, kind of like the rules of a game. It's the official language that all devices use to send and receive data correctly. So an IP address is simply that unique identifier that follows these rules, allowing your devices and some distant server to find and talk to each other. Without it, the internet would just be a jumbled mess of lost data.
Now, this system wasn't built perfectly right from the start. As the internet absolutely exploded in popularity, the original address system started to, well, run out of room. This led to a super critical upgrade. So let's take a look at the old version versus the new one.
On the left, you've got the original, IPv4. Its structure gave us about 4 billion unique addresses. Now, back in the early days of the internet, that seemed like an absolutely enormous number. But as more and more devices came online, we are heading for what was basically a digital housing crisis. So we upgraded to the system on the right, IPv6. And the leap in scale here it's just staggering. We went from a 32-bit system to a 128-bit one, creating a pool of addresses so big it's actually hard to wrap your head around.
Yeah, that's 340 undecillion. To put that in perspective, that's more than enough addresses for every device, every sensor, every smart toaster, and literally every grain of sand on Earth for, well, the foreseeable future. This number just brilliantly shows how future-proof the new system was designed to be.
Okay, so not all IP addresses are created equal. They also come in different flavors, depending on what their job is. First up, let's look at the difference between a public and a private IP. And to understand this, we can go right back to our mailing address analogy. Just imagine your entire home network. Your router, your laptop, your phone is one big apartment building.
Your public IP is like the main street address of the entire apartment building. It's the one address the rest of the world sees, and it's assigned to you by your internet service provider. But inside that building, your router needs a way to get the mail to the right apartment, right? That's where private IPs come in. They're like the individual apartment numbers for your laptop, your phone, and your smart TV, so your router can direct traffic correctly within your home network.
All right, so beyond public and private, there's another key distinction we need to make. Is your address permanent or is it temporary? And this brings us to static versus dynamic IPs.
A static IP is exactly what it sounds like. It's fixed. It never changes. This is absolutely essential for something like a website server, which needs a reliable, permanent address so people can find it. But for most of us at home, our needs are temporary, so we use a dynamic IP. Our internet provider assigns us a temporary address from a big shared pool. It's way more efficient and cost-effective for them because they can just recycle the addresses as users come and go.
So how does this dynamic system work? It's all handled by something called the Dynamic Host Configuration Protocol, or DHCP. Now that's a mouthful, but just think of it as the friendly receptionist inside your router. When you connect your phone to the Wi-Fi, the DHCP receptionist looks at its list of available addresses and lends one to your phone for that session. When you disconnect, the address goes right back into the pool, ready for the next device. It's a super efficient way to manage everything.
So, we've covered versions and types, public and private, static and dynamic. But let's zoom back out. Why is understanding any of this so important? Because this entire system is the bedrock, the absolute foundation of how we communicate online.
This quote here, it really gets to the heart of it. An IP address does two fundamental things. It provides a location, kind of like a digital zip code, and it makes your device reachable. Without both of those, sending an email or streaming a video would be totally impossible.
It provides both a unique identity and an open door for communication.
All right, let's do a super quick recap of what we've covered. First, IP addresses are the unique mailing addresses of the internet. Simple. Second, the new IPv6 system gives us a nearly limitless supply of those addresses for the future. Third, your network uses one public IP for the outside world and many private IPs for all the devices inside. And finally, most of us use dynamic, temporary IPs that get efficiently recycled.
And that leaves us with a final thought to chew on. The big leap from IPv4 to IPv6 was all about solving the problem of scale. But as we move into a future with billions of interconnected devices, the Internet of Things, what will the next protocol need to solve? Will it be a problem of speed or security, or maybe something we haven't even thought of yet? It's a fascinating question about the very foundation of our digital world. Thanks for tuning in.